Okay, we'll get started. Hi everyone, my name is Ashutosh. I am part of the open source software group within ARM, and I tech lead the TFM project within ARM. Today we are going to talk about some introductory level details about the PSA and some architectural details about the Trusted Firmware M project. After which we'll walk through some of the secure service designs, and time permitting we'll walk through some of the use case scenarios to see how it all fits together. And at the end, some conversation about how you can contribute to this project. I would like to make it a very interactive session, so if you have a question or if you want to make a point, please stop me at any point you feel like. All right, let's get started. PSA. PSA was launched sometime in the end of 2017. From the technical standpoint, it has three main aspects. First is understanding what we are trying to solve, understanding the threats that exist for the connected devices space, analyzing the problems that we can solve and that we should be solving, and that leads to the second stage, the architecture. Based on our understanding of the problems that or security issues that exist or may come up in future, we are trying to create a set of architecture specifications that will govern how the software should operate. And to support the software architecture, you need to have some hardware backing, some hardware features that will allow the specified architecture. And that's governed by the hardware requirements. You will be seeing specifications about the mandated hardware features, what kind of keys you should have, what kind of peripherals you should have to support the different compartmentalization that we want to put in the whole system. And finally, the architecture leads to implementation, which is what we are going to talk about in today's presentation, the TFM project. Before we get into the details of the TFM project, there are some underlying principles which basically which come across for most of the use case scenario, for most of the use cases we want to develop for the connected devices. First being the secure boot. We want to make sure that the software that runs on a device is not tampered with. It is what it claims to be, and that is ensured by the trusted boot part of the system. So that's one of the underlying principles that is required for any connected device. The second part is non-mutable device identity, non-mutable and secret device identity, so that everything that happens on a system can be tied to a specific device. And the third aspect, the third underlying principle for most of the use cases is updatability. We understand that the software is always, or most of the time, has issues. And the way, with the evolution of threats in the, that exist for connected devices, the software also needs to evolve, it needs to change, it needs to fix. And for that, we need to be able to update the software that is running on a device securely and remotely. And lastly, any transaction that happens on a device or any communication that happens on a device should be authenticated through cryptographic certificates. So these are the four basic principles which I think apply to most of the use cases that we'll have in connected devices. TFM. TFM is the open source implementation of PSA. It is targeted for Cortex-M devices. Currently, we have support for Cortex ARMv8-M architecture. We'll be adding support for other M architectures as well going ahead. If you look at the block, this block, the left-hand side represents the classical system, where you have a scheduler running on the device, which is assisted by some software libraries, your TCP/IP stacks, your mathematics libraries, and then on top of it all, you have the system firmware, the application. So that's the classical view. On the right-hand side, you see the right-hand side represents what you have, what we have in the TFM. Most of the software that implemented in TFM is represented on the right-hand side. The underlying principle for the architecture definition for the TFM is principle of least privilege. What that means, the software need to be broken down into the small pieces, and each small piece should be given just enough privilege, just enough access to let it do its job. We'll get into the details of the different blocks in the rest of this presentation. But let's have a quick look at what we see here. On the bottom right side, you see the bootloader. Bootloader is responsible for securing the software that executes on device, making sure that the software is not tampered with, it's not rollback, it's not altered in any fashion. It also participates in the firmware update process. Time permitting, we'll go through the update process as well and see how bootloader, what kind of duties bootloader performs in that update operation. And thirdly, it collects attestation information, attestation data for a specific device. What that means, that again I'll cover in one of the later slides. So if you look at the other block on the bottom, the TFM framework, this is the runtime framework which provides the compartmentalization for the rest of the system. It provides the so it does initialization of the secure peripherals. It creates sandboxes for the rest of the system. So if you have different services running on the system, they will be running in their own isolated domains. It also provides facilities to handle interrupts securely, and then some mechanisms to do crash handling and recovery from crash. And once it has done the initialization of its own and the initialization of the partitions that are running on top of the framework, it passes on the control to the non-secure side. And from then on, all of the transactions are initiated by the non-secure callers. So non-secure side of the software can make calls into the secure side and so on and so forth. Before I go ahead, is there a need to look at the details of V8M architecture, or is it okay to assume that we all fairly understand how V8M architecture operates? Okay, I take that as a yes, and I assume that you are all experts on V8M already. Right. This is a different representation of the same block, same picture we saw in the earlier slide. This is more of a functional representation and how the system is divided into different building blocks and why they are colored differently. There is a reason why they are colored differently. If you look at the bottom, there are yellow boxes. They are the hardware blocks of the system. They represent the bare minimum that you need to have on a system to secure the device, to basically, so that's again governed by some sort of compliance, some sort of specification, and that's called TBSA. The TBSA specification says that these are the minimum set of hardware and the hardwares that you need to have on a device, and these are the characteristics of these devices that you must have for the device to be a TBSA compliant device. All of the access to the TBSA component is done through the TBSA HAL API. So this is again a lightweight HAL that provides a unified access to the platform, unified access to the hardware, the underlying hardware. The boxes above the HAL API, you have the bootloader box and the framework. We'll talk about these two boxes in a bit more detail. The blue boxes in the middle, they represent trusted services. So there is a concept of trusted services and secure services. The trusted services, they represent they represent a bit more. What they actually do is they have access to the device's root of trust. So in a sense that they control the overall security of the system. So if there is a bug in one of the blue boxes, it essentially leaks some really serious security information about the device. And for that reason, they need to be thoroughly vetted, thoroughly reviewed, thoroughly analyzed from security threats. Having said that, all of the blocks on the right-hand side need to be thoroughly reviewed and thoroughly vetted, more so the blue boxes. The key point here is blue boxes provide services to a very limited set of entities. They are not general purpose general purpose services that can be called from rest of the system. They provide a very specific functionality, and that functionality is limited to a very limited set of entities just on the secure side. And so the limited set of entities would be one of the green boxes you see on the top. The green boxes, they represent the generic secure side endpoints that can be called from the non-secure side as well. And they can be called from the non-secure side, they can be called from other green boxes. So there is a layered approach to the overall architecture. As I said, it operates on the principle of least privilege. The software components which require access to the root of trust, they are sandboxed as one of the blue boxes, and the rest of the system is built on the top as green boxes. Yeah? Mm-hmm. Sorry, if you can.
Yes, regarding the hardware access, so on the low layer, in this model, there will be accessed in secure privileged domain. If the layer in green needs, for instance, to use any hardware accelerator.
Yeah, yes, I have an answer to that in one of the later slides. The answer is yes and no. Some of the blue box APIs which are exposed by the TBSA HAL will be accessible only to the blue boxes above them. But there are cases and there are ways they can be exposed directly to the green boxes. I'll come to that in one of the slides later on. So I'm going to pick each all the different blocks one by one and try to explain how they behave and what their responsibility is. And yeah, let's start with the TFM core framework. This is the boilerplate for the runtime software, and it provides the sort of environment for running the non-secure side software, running the secure side services, and it creates the isolation profiles. So based on what you define at the compile time, the framework will generate a database of what different partitions you have in the system, which one of these is secure partition and which one is trusted partition, create the hardware profiles for the database which is generated, and enforce the isolation profile which we have defined in the software using the hardware features. So that's one of the main functionalities of the blue box in the bottom. It also provides a way of communicating between different entities. So now that we have sandboxed the different blocks here, different software entities, they need a secure way of talking to each other. And that is provided by the framework in form of IPC. All right, so let's move on to the next one. So that was a brief idea about what the framework does. I'm going to cover some of the changes we have done in the recent past and some of the interesting details, in fact, because there are too many to cover in a 1 hour slot. One of the important changes we have done is transition from the non-secure world to the secure world. In the earlier implementation, the transition was done in the handler mode. So what that means, if non-secure side wants to make a call to the secure side, it first needs to raise a SVC so that it can get into the handler mode. And from the handler mode, it can do the transition to the secure side. Now, this has a couple of problems. First is it blocks the whole of the non-secure world. In most of the scenarios, the SVC handling on the non-secure side will run at a higher privilege than most of the interrupts in the system. What that means, as long as the call is active to the secure world, non-secure side cannot schedule. It cannot schedule anything else in the system. It can probably not even handle interrupts. And so, which means real-timeness of the non-secure side is kind of lost. By making the transition in secure world, transition to the secure world in the thread mode, we solve that problem. Now the transition happens in the thread mode. So ideally, if you have interrupts which have priority defined properly, they can preempt secure side service execution, and then you are back to having the real-timeness on the non-secure side. The second problem is the veneer code. Now, veneer code is the gateway function that kind of allows transition from the non-secure side to the secure side. And the gateway code in the earlier implementation was run in the handler mode. The problem is, if there is a bug in the handler in the veneer code, and if you have too many veneers in the system, it becomes a little difficult to vet them all. So if you have a bug in the veneer code, that kind of exposes the whole system, because the veneer code is being run in the privileged mode, and it has access to the whole system. So one buffer overflow, and all of the security is lost. So doing the transition in the handler mode, in the thread mode, solves that problem as well. The veneer code is now executed in the thread mode, thread non-privileged mode, which means even if there is a bug, the effect of that bug is limited to that veneer code implementation. The second thing we have implemented is a manifest-based service definition. It's partially done. What this means is, go on.
How does the transition happen now? So it happens in thread mode, but so I think what I would like to hear a little bit more about what happens now when it crosses the boundary in the thread mode.
So when it crosses the boundary, it is, so let's say on non-secure side, you have applications. Application is running in the thread mode. Now, it doesn't need to get into the SVC handler mode on the non-secure side. It just makes a veneer call directly to the whatever veneers you have defined in the system. The thread can directly make a call to the veneer. The veneer basically is still running in the thread mode. It does some sort of some verification of the call, and if the call is OK, then it will raise another SVC on the secure side that will take the control to the partition manager on the secure side. The partition manager on the secure side will now decide what that call is meant to do, or where that is intended to be terminated at. So the call is essentially targeted. The call must be targeted to a specific service. The SPM, which is now running in the handler mode, will schedule the call service again in the thread mode, and that's where the call will land in. The service does what it's supposed to do. It finishes its job, tells it back to the framework by raising another SVC, saying that, yeah, I'm done. Whatever you requested me to do is finished. The SPM, which is again running in the handler mode, does cleanup. It verifies that whatever the service is saying is true, then replies back to the non-secure caller in the thread mode. Is that what you were asking? OK. OK. Yeah, right. So second thing is manifest-based service partition definition. What this means is you can define a partition, a service, in using a manifest file, which is written in YAML format, YAML format. This is not completely implemented. There are certain parts which are still hard-coded in the code, but going ahead, it will be cleaned up. And essentially, when you want to define a service, you write your C code. You basically expose the service to the rest of the system using the manifest file, and the build system will automatically take care of generating the whole data structures and pulling in the service in the right way. Third major thing that we implemented from the last time we spoke is IPC. IPC is the PSA defined way of communication between different entities. That is upstreamed now. We have the full GCC support now for all of the platforms that are there in the code base. They can be compiled using ARM-CC or using GCC. So yeah, that's completed. We have done some improvements to the HAL abstraction, and then we now have support for ARM-V8M mainline and baseline process. Some details about the IPC. IPC, it provides secure way of communication between different entities. These entities could be two secure entities trying to talk to each other, or a NSP entity, the non-secure side entity, trying to talk to a secure side entity. And the IPC ensures that the communication itself is secure, and any misformed request from one side doesn't lead into overall system vulnerability. If you have to visualize how a service would be run, how a service looks like in IPC mode, it is like a daemon running in a while loop, and the calls from the client are passed on as a message to that daemon. So daemon is running, it's waiting for some messages. When a request from the client comes in, the request is composed as a message to the targeted partition. The targeted partition basically receives that message, interprets that message, and does whatever is required, whatever the call was made for, and then it replies back. This also means the interrupt handling the interrupt handling part of the partition will be synchronous to the execution of the partition or service. The service is running in a while loop. If an interrupt comes in, that interrupt is again passed on as a message to the partition or other service. And so it becomes kind of synchronous to the flow of the service. And what that means, you don't have reentrancy in the partition code. All of the calls, all of the APIs implemented in IPC are blocking calls. So yeah.
I remember Linaro was looking at OpenAMP for the IPC. Is this based on OpenAMP, or is it a different IPC?
This is slightly, so I think the confusing term here is IPC. The OpenAMP part is about standardizing communication between two different CPUs or two different heterogeneous systems, A plus M, or maybe even 2M devices. This is slightly different. This is slightly more abstracted. So for example, if you have a PSA compliant system which implements IPC, you could have OpenAMP implementation, and on top of that, you'll have this PSA IPC. So it's the physical transport layer is implemented by will be implemented by the OpenAMP, and then you have another layer on top of it, which is the PSA IPC. Right. Yeah, Manish.
Non-privileged. What happens if I have services in the secure world that are really, really long, take a really long time, like primality tests for RSA keys? What is going on to make sure that the non-secure world isn't completely blocked for multiple seconds?
So there are two parts to this question again. One is what happens to the caller itself. So if you have a task on the non-secure side which made the call, that task is blocked. It can't do anything else for that duration of the call. But the rest of the system is not blocked. It can still schedule other threads on the system. It can do other activities that it needs to do. The other aspect is the service side. The service side is not required to process all the requests serially. So for example, if you're doing a crypto operation, and after initial housekeeping, if a crypto accelerator is triggered to do the actual job, the service is not mandated to finish the old task before picking on the next one. So a service implementer can still decide to pick multiple requests at the same time, one after the other, based on its hardware capabilities and the software capabilities. Yeah? Right. Some of the security considerations about the IPC, all of the APIs, the calls on no, let me rephrase that. The transactions between different entities is based on IOX. IOX is a structure which is just a pointer and a length. So basically, the framework, the TFM framework, it cares about the buffer that you're passing and how big that buffer is. What that content is not interpreted by the framework. That is the agreement between the two endpoints that are trying to talk to each other. So having the communication based on IWEC, it allows all transactions to be vetted by the framework. So a caller cannot pretend to own a memory that it doesn't have access to. So the framework will make sure that the IOX that are being passed to the other side, they belong to the caller and they are sanitized, and if not, then the call will not go ahead. After that, the validation happens after the IOX are integrity protected. What that means is they are essentially copied into the secure domain, into the privileged code. So this is to prevent talk-to attacks where after verification of the IOX, if the malicious entity goes and changes the content of the buffers, the rest of the framework and the call service is protected against those malicious changes in the background. Right. Other thing is all of the accesses to the client memory is API based. The service cannot directly access the client memory, and any read or write to the client memory is through API, and API is again streaming-like API, so you can't read the same client memory location twice. And finally, all of the accesses to the peripherals are done through MMIO regions. So any partition, any service that want to make an access to a peripheral doesn't need to go through the privileged code to make that access. Each service can have its own pocket of memory mapped regions, and those pockets basically represent the peripherals they own. What that means is even if a service is running in the non-privileged mode, it can still access and manipulate different peripherals. So this was a brief introduction to IPC and some of the features. In tomorrow's talk, I'll try to see if there's a need to get into a bit more detail on the framework aspects. So if you have questions, we will have some more time again tomorrow to talk about the framework. Let's have a quick look at some of the services that are implemented so far in TFM and how they are architected. Excuse me. First one is crypto service. The underlying principle behind crypto service is limiting the scope of cryptographic keys in the system. A device could have multiple keys, and you don't want that key to be visible to the whole system. You might want to be able to make use of it from the whole system, but the key itself should not be exposed because that exposes a bigger threat to the overall system. And that attack could not be just limited to the device. It could mean, if you have a class key, that class key could mean attack on the other side of the infrastructure. So the underlying principle is hiding the keys from the system, at the same time making sure that the system can make use of these keys. Then again, it's a multi-layered question. It's a multi-layered problem. Not all keys are same in the system. If you look at the bottom of this picture, the yellow boxes represent hardware keys. And these hardware keys could be coming from different entities in the supply chain. There could be some keys coming from the chip manufacturer, keys coming from the device manufacturer, keys coming from a third party. And they all don't share the same level of trust with each other. So it is required to make sure that the accesses to the hardware keys is limited. They should not be able to see from most of the system. At the same time, they should not be even usable by all of the system. If you're talking about a chip manufacturer's key, if a software entity wants to make use of the chip manufacturer's key, it has to prove that it is authorized entity to make use of that key. So that's why you see, so as I said, it's a multi-layered problem. Now, when you move away from the hardware keys, there will be software keys based on the use case that will be stored in flash through secure storage. They have a different level of security requirements and different level of visibility requirements. So that's why the crypto service is intended to be split into the blue box and the green box. Blue box in the middle basically represents the part which handles the hardware keys and abstracts the uses of the hardware keys, so it can vet who is making the call and who is trying to make access to the hardware keys and make sure that it doesn't fall into the wrong hands. It also provides abstraction on top of the hardware accelerators. So if you have hardware accelerators which can offload the cryptographic load from the CPU to a accelerator, this abstracts that part. So the higher level of the software doesn't need to change based on what we have in a typical silicon. The green box on the top, and again, the blue box is again the access to the blue box or calls to the blue box are limited to very specific entities on the secure side, just to make sure that the hardware keys are not being usable by, they cannot be used by malicious actors. The green box, this provides the user-facing APIs that can be used by rest of the systems. The rest of the system includes the non-secure side. So a non-secure side can make a call to secure side, and that call will land into the green box. The green box will decide what to do with that request for the cryptographic operation and basically act on that request. The green box can be called by other green boxes as well on the secure side. So this is a very high-level view of what TFM's crypto service will look like. We have a primitive implementation in upstream, but yeah, this is the final picture. The crypto service is complemented by secure storage. Secure storage provides a confidentiality, integrity, and authenticity protected way of storing systems security critical assets. It makes sure that what it makes sure is that even if the underlying physical medium, the physical storage medium is not secure, using cryptography, the plain text visibility of keys and the cryptographic assets is limited again to the secure side software entities. The secure storage is tied, as I said, it uses cryptography to do the confidentiality, integrity, and authenticity protection. And it uses AES GCM to perform that operation. And the AES GCM operation, again, is tied to a hardware unique key derived key. So that if you plug out the secure storage from one device and try to plug into another device, it will not work because it is signed to a unique key for that device, signed and encrypted using a unique key on that device. And that unique key will be different on a different device. The secure storage, again, leverages on the blue box of the crypto service. So remember I said in the slide that the blue box is limited to very few entities. This is the other entity which can make use of the blue box of the crypto service. There are two reasons for that. The secure storage service needs to make use of hardware unique key. So the blue box provides an abstraction and a key derivation tree for hardware unique key. So it makes sure that the secure storage is given its own derived key, and it maintains a key hierarchy so that two entities on the system which wants to make use of hardware unique key do not end up having same key, or do not end up being able to derive the same key maliciously. So that's the reason one. The reason two, if the green box here makes call to the green box on the green box of the crypto service, there is a cyclic dependency here. The crypto service needs to make use of secure storage to access the assets which are stored in the secure storage. At the same time, secure storage needs to make use of crypto service to decrypt the content. And the framework doesn't allow this kind of cyclic dependency because the calls are blocking. So having this blue blocks also solve the cyclic dependency problem. There's another important aspect to secure storage. We have implemented a file system. So this is a file system which is highly optimized for embedded applications, and it does a very specific job. At the same time, the file system is abstracted. So there are clear interfaces defined. And if a use case requires a bit more sophisticated file system, and the system's requirements are a bit more divergent, then a different file system can be plugged in while still making use of the rest of the secure storage solution. The third service, audit log. Audit log provides protection against repudiation attacks. What this means is if, let's say, there is a point of sale device which handles financial transactions, and some financial transaction was initiated by an entity, and later on that entity declines that it even ever tried to make that transaction. Now, audit log makes sure that the system's security critical events are logged so that the original initiator of the request cannot deny it. And it's logged in a way that is integrity protected and confidential and authenticity protected. So an entity which made a call cannot deny later on that it made the call in the first place. What is logged is not defined by the audit log. This is highly use case dependent. The use case developer has to decide what is the security critical event of the system, and need to decide what should be logged, what shouldn't be logged. The audit log service also provides a secure retrieval of the audit logs so that it can be securely transported to a server which can analyze these logs and make some, can do some analysis or do some postmortem based on the content of the audit log. So we are running quite late on the schedule. Let's see if we can. I'm going to skip the bootloader part. We can cover some of this tomorrow if there is a specific interest. But for today, I'm going to skip this. And just in the interest of time, I have few use case scenarios. Let's see how many we can cover. And if you have a specific question on the rest of the use cases, we can talk afterwards as well. The first is runtime device provisioning. What runtime device provisioning is meant to do is provide a secure way of, as it says, provision the device. What this means is if you have certain contents stored in the secure storage, you should be able to securely update them over the air through some commands from the server. And any malicious actor in between should not be able to tamper with the whole transaction. So a typical flow could be a provisioning request comes from the server, says that I want to provision new assets on the device. The assets could be your PSK TLS keys, it could be your provisioning keys, or it could be any other use case specific asset on the device. So the server sends a command to the provisioning client on the non-secure side. The provisioning client tells to the provisioning service on the secure side, hey, there is a request for provisioning, what should I do? The provisioning service replies back with a challenge. It says that here is a token. If you want to send me a provisioning command next time, or a provisioning blob next time, you better sign the blob with this challenge. The provisioning client will take the challenge and pass it on to the cloud. Cloud will take the challenge now, get the blob, get the provisioning blob, which will include the provisioning keys and all the data that need to provision in some format, and take the challenge, sign it together, encrypt it together, and pass it back to the provisioning client. Provisioning client passes on the same blob to the provisioning service on the secure side. Secure side performs an authentication check, and it has a reference to the old challenge. It can compare the challenge, and it can perform the authentication on the blob. And if it all matches, it goes ahead and updates the content of the secure storage with the new assets. I'm going to skip this one as well. Attestation, I promised to talk about attestation a bit in the earlier slide, so I'll try to cover this as quickly as possible. Attestation is a way of passing on device-specific information back to the server and providing some critical information about the device to the remote entity. What this information could include is the boot signature of the device, how much time it took to boot, what was the image signature that is being run on the device, what is the device's identity, what is its geographical location, and it could be any other vendor-defined attestation data. This helps in assessing the device's sanity and assessing what's running on the device and assessing that whether it's compromised or not. And if the device is compromised, then these attestation data will tell to the remote entity that, hey, there's something has gone wrong, take some corrective actions. And that's for the remote entity to decide what to do next. It's fairly similar flow as the earlier one. The cloud makes a request for attestation. It says that can you send the attestation data back to me? It again comes to the client on the non-secure side. The client passes on the request to the secure side. It also passes on the challenge that server would have given to the attestation client. The attestation service would have collected the data in advance. Some of the data it may collect in the runtime based on vendors' own specification about the attestation data. The attestation service will collect all this data, the attestation data, combine the attestation data with the challenge that came from the server, sign it together, encrypt it together, and pass it back to the server. And the server can now basically authenticate the blob and decrypt, and it doesn't always have to be encrypted, but it must be signed. It must be integrity protected. So the server decides whether the data is compromised or not. If the data is not compromised, then it will go on and evaluate what's the content, and on that basis, it can take the next corrective action or whatever it need to do. So how are we doing against time? We have 10 minutes left. So this is a slide about how you can get involved in this project. There's a lot of documentation in the trustedfirmware.org website. You can talk to us. I will be sitting in the light hacking room most of the time. So if you want to discuss something, I'll be there. And if you want to schedule a meeting, you can schedule a meeting as well. A very quick look at what is coming up next. The current IPC implementation is still in a feature branch in our code base. At some point, it will be merged back into the master branch, and all of the existing services will also support the IPC model of the communication. Then there is prototyping work going on for the secure side interrupt handling. We don't, the current code base doesn't allow secure interrupt handling yet. I think in next quarter we should be able to see some level of implementation there. Then there is a scheduling aspect of the TFM. The current implementation allows single call to the secure side, and that again is a blocking call. It cannot come back until it finishes the whole thing. So yeah, what this means, if there is a transaction being triggered on a secure hardware, let's say if you're trying to do some crypto operation and the crypto operation is actually being done by crypto accelerator, the CPU is free, so CPU can do something useful. Currently, it cannot go back, but if we introduce some scheduler features, the CPU cycles can be reused to perform another non-secure side operation. Then there are enhancements planned for the secure service, crypto service, which includes the handling of asymmetric cryptography, and yeah, and the general evolution of other services. The attestation service is kind of being designed right now. We should be able to see some level of details in the next quarter. Then the definition of provisioning service is going on. We should again be able to share some details next quarter or in Q1. There is a standardization work going on about the TBSA HAL APIs. So to ensure that the migration from one platform to another platform is as painless as possible. And then we are also creating threat models for the different aspects of the TFM software. They will also start appearing in the TFM code base or in the Trusted Firmware website. Last few minutes to ask some more questions. We have three more sessions planned. There's one BOF session about the IoT security. That again is a very open session. I don't have a lot of slides for that. I'm hoping that we'll have more dialogue and it will be more discussion-driven session rather than me trying to present some slides. Then there is a generic project update, the Trusted Firmware project update. And there are some other discussions around Trusted Firmware CI. Yeah? Sorry.
How is the software in the secure privilege domain updated? Or is that something that's done as a root of trust one-time flash?
So very good question. Let me see if I can navigate to the right. Yeah. Right. So this has multiple aspects. There is a non-secure side aspect which can interact with the server to fetch the updated blog on the device. Now, it's possible to just fetch the new firmware from the cloud, put it on the flash directly in a different slot, and let the bootloader decide whether it's a valid firmware or not. That's one option. But that can open a lot of attack vectors, and it may wear out the flash. And if, let's say, some malicious actor is able to manipulate the non-secure update client to write to the flash, then essentially you are wearing out the flash. And that could be a potential attack vector. So the update client downloads the firmware, makes sure that it is its signature, its cryptographic signature is all right. It's matching with what it says. And then only it programs the binary blob into the flash. And the signature check part is done by the secure side of the software, the crypto service that I mentioned. So that's the update. That's where the job of the update client finishes. But so far, the image is just sitting in a flash. It's still not being used. Once the image is downloaded, it will trigger a reboot of the system. So when the bootloader comes in play, it sees, there's a new image. Let's do something with it. Now it will perform all sorts of checks on that image again. It will see if it has been rolled back image. Is it old image that was used in the past, or is it actually properly secured new image? It does all sorts of checks. And if it passes, then it swaps the images. The active image is basically swapped with the new image. And then that kind of marks the completion of the update process. There's another aspect to it. Let's say the new image is has some problems. You could have very device-specific problems, and that may mean that a firmware image, if it has not been tested properly on the development side, it may not work on certain devices. So there is a feature in the bootloader which allows you to say, yeah, image is fine in the runtime. So when the firmware is booted up, you can perform some built-in test to check if the new image is booting fine or not. That sets some flag on the device, and that's when the whole boot update operation is considered complete.
Thank you.
Hi, actually, just on the, you mentioned earlier about this glue API between to the crypto service.
Okay.
I was wondering, is this just an internal TFM thing to provide, API between the various services provided by the TFM project, or is it a more open API that other services could be built upon?
Let me try to get back to the slide. Right, so I guess you're talking about the TFM Crypto Glue API. This is again on top of the IPC. So if you're following the IPC model of the communication, this will have IPC underneath, and then there'll be C libraries built on top of the IPC. So the communication method is still the standard communication method, which is used for communicating between two different blobs on the secure side. What Glue API means here is some sort of C file abstraction on top of that bare IPC.
Yeah, I was just wondering if, when there's a new version of TFM, are you free to just change those APIs as you like, because it's all part of the TFM project, or do you need to maintain compatibility potentially to other services not provided by the TFM project?
So at this point, I don't see a hard problem. I don't see a very complex problem there, because it's still, as I said, it's all TFM. The part that impacts to the rest of the ecosystem is the TBS HAL APIs. And basically, the blue box might have some tying up with a specific platform. But the Crypto Glue API is, as I said, is more TFM internal. However, it will evolve as any software does.
Okay, thanks.
Yeah. Okay, last 3 minutes.
So regarding the update of software, so the last slides, you imagine only to update software process element, or including the SPM can be updated?
Yeah, yes. So, wait, let me try to get to a bigger picture. Sorry, I don't have my laptop here, so I really need to click. Yeah, so in this, everything is updatable. Whatever you see on the in this whole picture, everything is updatable. There is a debatable part which is bootloader. So if you split the bootloader part into two, select the ROM code and the updatable part of the bootloader, then the bootloader itself is updatable, because there is another fallback in the ROM. But there's another topology possible where you say bootloader is simple enough, last words, famous last words. And we say that, yeah, this is good enough. I mean, you have vetted the bootloader code, it's going in the silicon, in which case only the rest of the software is going to be updatable.
So,
okay.
But on this update, so it means currently on the MCU bootloader there is no encrypted part. So you imagine that in the update there is no things hidden on the software received?
not
Or it
sure
will be it will be, I mean, on the update part received by the target. Everything is in clear, or its application will decrypt before installing, or
Are you talking about the case where the bootloader itself is updatable? Or so the update client, it doesn't have to decrypt. It doesn't even have to do integrity check. In theory, it can just download whatever is being sent by the server and dump into the flash. But as I said, it has some attack vectors. So it is nicer to validate the image in the update client by using crypto service before dumping into the flash. And that's all the update client need to do. At that point, you reset the device, bootloader comes into play. It sees that there is a new image in the flash, and that's where it's going to decrypt and basically integrity check again the firmware and program it again. Okay, thank you everyone. I think we have another session tomorrow, so if you have more questions, we can talk tomorrow. Thank you.